Hi all, welcome back to another Engsci recap video, and today I'll be going over the course MAT185 Linear Algebra. My name is Jason, and I just finished my second year of engineering science at U of T. So what is MAT185? Well, it's a class I took in my first year, winter term, and when I took it, the instructors were Professor Sean Uppal and Professor Gabriele D'Eleuterio. So the main course topics, being a linear algebra course, we covered more of the sort of abstract concepts related to linear algebra. In the fall term of first year, we mainly dealt with computational linear algebra, working with vectors and such, but here we cover more abstract concepts like vector spaces, subspaces, bases, row and column spaces, rank and the dimension formula, coordinates, change of basis, determinants, eigenanalysis, diagonalizability, and linear differential equations. So today I'll be going over one of the questions from term test 2, which I took on March 25th, 2021. This question covers the subspace test, dimension of a subspace, as well as properties of the determinant. So this is the question. It's relatively simple. It has two parts, A and B. Um, Basically, it says we have a set of vectors represented by W. And W is the set of vectors uh, which are 1 by n, such that the determinant of this matrix is equal to 0. And A1 all the way up to an minus 1 are vectors that are also in Rn. So we have a square matrix here whose determinant is equal to 0, and the set W is all the vectors x that also belong to Rn and fit this determinant condition. So the first part of the question, part A, we want to show that W is a subspace of Rn, and in part B, we want to know what the possible values of the dimension of W are. So to recall, in order to do a subspace test, we need to show that we have a valid zero vector. We want to show that our set of vectors has closure under vector addition, as well as under scalar multiplication. If we can show all of these things in Rn, we can show that W is in fact a subspace of Rn. So first of all, we want to show that we have a zero vector. And obviously, most of the time, we will attempt to show that the zero vector is just a vector of all zeros. So we'll attempt that right now. So we have a 1 by n vector of zeros. And we should see that the determinant of this matrix is going to be 0. And that's due to the property of the determinant, where if we have a 0 row, we will have a determinant of 0. So indeed, this zero vector belongs to W, and so therefore we have a zero vector in our set. The second property we want to show is closure under vector addition. So let's define two vectors, x1 and x2, to belong to W. We want to show that the determinant of x1 plus x2 is equal to 0. The way in which we do this is we use this property of the determinant, where if we have the sum of two vectors in one of the rows, we can simply split the determinant into two other vectors, where the determinant of this matrix is equal to the determinant of this matrix, where the last row is simply x1, and add this to the determinant of this other matrix where the last row is just x2. And we keep all the other rows the same. So this is a valid property of the determinant. And we should notice that because x1 and x2 belong to W, these two terms will both be equal to 0. So their sum will also be equal to 0, which shows that the determinant of this matrix, where the last row is x1 plus x2, is equal to 0. And so we have shown that x1 plus x2 belongs to W. So we have closure under vector addition. The final property we want to show is that we have closure under scalar multiplication. So we let vector x1 belong to W, and we choose just any arbitrary scalar lambda to be part of R. And we want to show that the determinant of this matrix, where the last row is lambda x1, is equal to 0. And the way in which we do this is we use the property of scalar multiplication for the determinant. We can bring out this scalar multiple in front of the determinant for a single row. We leave the first n-1 rows the same. And since we know that x1 belongs to W, the determinant of this matrix will simply be 0. So lambda times 0 will also be 0. And therefore, we have shown that lambda x1 belongs to W. Since we have shown that W satisfies the subspace test in Rn for all three of those properties, we have verified that W is in fact a subspace of Rn. Now, for part B, we want to find out what the dimension of W is. And there are two cases we have to consider here. The first case is where the first n-1 rows are dependent. The second case is where the first n-1 rows are independent. There are no other cases to consider here because, a set of vectors is either dependent or independent. There's nothing else. There's no other case. So in case 1, the first n-1 rows are dependent. Therefore, the determinant of this matrix is going to be 0 for all x, no matter what x is. And that's because there's a property of the determinant. If your rows are dependent, then the determinant will be 0. Therefore, the dimension of W will be equal to the dimension of Rn, because x can be any vector in Rn, and so that is simply equal to n. In case 2, the first n-1 rows are independent. So if we want to satisfy this condition where the determinant is equal to 0, we know we have to have a case where the matrix is not invertible, which implies that the rows are dependent. But since we know that the first n-1 rows are independent, x must depend on these first n-1 rows. Therefore, x is spanned by a1 all the way to an-1. And therefore, these n-1 vectors span W. But we also know they're independent. And if they span the subspace and they're independent, then they must be a basis. Thus, the dimension of W is simply equal to the number of basis vectors we have, and because we have n-1 basis vectors, the dimension of W is n-1 in this case. So our final answer is that the dimension is either n or n-1, depending on whether the first n-1 rows are dependent or independent. So before I end off this video, I'd like to make some quick acknowledgements. I'd like to thank Professor Zhang Uppal and Professor Gabriele D'Eleuterio for the course and the term test content. I'd also like to thank my tutorial TA, Xintong, and as well as the individuals who I drew inspiration from for this Beamer template. But thank you very much for watching, and I'll see you next time.